So this week we are talking about z-score transformations and normal curves. Now, a z just isn't the mark that Zorro used to make. It's important in statistics. It's important because sometimes we want to use standard deviations, but we want to compare apples to oranges. We want to compare different things. And so when we're working with a normal curve, we'll be looking at how we do z-score transformations. Okay, so let's pop over to the next slide. And this is kind of an introduction. Let's assume you got a 76 on a statistics quiz. Of course, you guys are all going to do much better than that. Is this good? You may be among the best of your class, but you could be among the worst. It helps to know the average, the mean, but is this sufficient? The mean alone doesn't show you the shape of the distribution, right? You still don't know where you're located on the distribution of marks for the entire population, which consists of all the students in the class. So the key question here is in order to assess whether your grade is a good grade, what's the average mark and how far or above or below the average is 76? In other words, what's your position in the distribution of marks for this class? Let's take a look. Two distributions of exam marks, one on the left and one on the right, A and B. For both distributions, the mean is 70. See, right here. Here's the mean, and it's 70. Here's the mean, and it's 70. All right. The standard deviation for one distribution, the standard deviation equals 3, and the other, the standard deviation equals 12. So in this curve, the standard deviation equals 3, and in this one it equals 12. The position of x equals 76 is really different for both of these distributions. Look, if the standard deviation is 3 and you got a 76, well, that means that you're way out here. You're like 2 standard deviations away from the mean. So you did really good. If the standard deviation is 12, that means that one standard deviation is all the way out here at 82, and you only got a 76, so you didn't do as well. A z-score specifies the precise location of each x value within a distribution. The sign of the z-score, plus or minus, signifies whether the score is above the mean, a positive, or below the mean, a negative. The numerical value of the z-score specifies the distance from the mean by counting the number of standard deviations between x and the mean. Here's an example. In a distribution of standardized IQ scores with a mean of 100 and a standard deviation of 15, a score of x equals 130 would be transformed into plus 2. Why? Because the standard deviation is 15, and 15 times 2 equals 30. You add 30 to 100, which is the mean, and you get 2 standard deviations, or z equals plus 2. The z value indicates that the score is located above the mean. It's on the plus side by a distance of 2 standard deviations, 30 points. 15 times 2 equals 30. Here's another example. In a distribution of income, how much money you make, with a mean of $30,000 and a standard deviation of $10,000, a score of x equals 20,000 would be transformed into, you already know this, don't you? Z equals -1. Why is that? Well, what's the mean? 30,000. So the z value indicates that the score is located below the mean. All right? So if I'm making 20,000 and the standard deviation is 10,000, a score of X at 20,000 means that I'm -1. I'm on the left I'm on the left side of the curve. Let me draw the picture. Here's the curve. Here's the mean. What's the mean? The mean is 30,000. The standard deviation is 10,000. Here's the plus side. Here's the negative side. So 10,000 is going to be one standard deviation. One standard deviation below. Here's one standard deviation above, and so it's standard deviation of 10,000. So the z equals -1. Here's another example. In a distribution of the weekly number of hours spent in the gym among John Jay students, of course, now that I'm at UNH, this should say UNH students, with a mean equal to 3 hours and a standard deviation equal to 1 hour, a score of x equals 7 would be transformed into, come on, give me the answer. What's the mean? Go back and figure out. The mean is 3 hours and the standard deviation is 1 hour. So if it's 7 hours, how much more than the mean is that? That's right, it's +4. So 7 plus 3 plus 4 equals 7. Okay, so the mean is 3, the standard deviation is 1 hour, so it's 4 hours or 4 standard deviations above. The z value indicates that the score is located above the mean. It's here's the mean. What's the mean? The mean is 3, and I'm way out here at 7, and it's definitely on the plus side. If it was 2, where would it be? It'd be on the negative side, right? But we're on the plus side, so it's 4 standard deviations away. Z equals +4. You're getting the idea that these z's are pretty easy, right? The z transformation, this is in a population, it's going to be a little different in a sample. The formula to change a raw score on X to a z-score, the number of standard deviations the score is above or below the mean, is z equals the X minus the mean divided by the standard deviation. Do you know how to figure out the standard deviation? My handy-dandy 6-step formula taught you how to do that, so you could figure out the z-score for any particular X value. And that's how you do it. You got to know the mean and you got to know the standard deviation. Do you know how to get the mean? Yep. Do you know how to get the standard deviation? You sure do. The z transformation in a population. The normal distributions can be transformed to standard normal distributions by the formula z equals x minus the mean. All right, so here's the original value. Here's the mean of the distribution. Here's the standard deviation of the distribution. And that gives you the z-score. The z transformation in a sample is slightly different. Are the numbers different? Negative. They're not. Just the symbology. Okay? Same principle, different symbols. The z-score equals the x, which is the same, minus x bar instead of mean, and divided by what? The standard deviation. So instead of using the small sigma, we use a big S. All right? Why are z-scores useful? Here's an example. Let's say Sandeep just got his marks for 2 statistics quizzes. Sandeep had a score of 50 on his first exam and a score of 50 on his second exam. We want to determine which exam he did better with. Let's compare them. If you know that the class mean for one exam is 40 and the mean for the other exam is 60, and that the standard deviation is 10 for both exams, which one did Sandeep do better on? In one case, Sandeep's exam score is 10 points above the mean. All right, Mean exam 1 equals 40, and the mean of exam 2 equals 60. In the other case, his score is 10 points below the mean. So it's important to interpret Sandeep's grade relative to the average performance of the class. So here are the two curves, and you can see where his grades are. He got a 40 and a 60. Sandeep's Z-score on exam 1, Z equals 50 minus 40 divided by 10 equals 1. 1 standard deviation above the mean. His score, Z-score on the second exam is Z equals 50 minus 60 divided by 10 equals minus 1. And that's 1 standard deviation below the mean. So where do you want to be? 1 standard deviation above the mean or 1 standard deviation below the mean? I want to be above it. Okay, so he did better on the first one. The example continued says that what if both distributions have the same mean? The class mean equals 40 on both tests, but different standard deviations. Standard deviation equals 5 versus standard deviation equals 20. Okay, tell me now which exam did Sandeep do better on. Still scores of 50 on both exams. So there it is. Sandeep's performance depends on how much spread or variability there is in the exam scores. There's not a lot of variability in this leptokurtic. It leapt up to the sky one, but in this platykurtic, there's more distribution. There's more scores. All the scores happen here, whereas there were more distribution of scores here. All right. So Sandeep's Z-score for the first exam, 50 minus 40 divided by 5 equals 2, as opposed to Sandeep's Z-score for the second exam, 50 minus 40 divided by 20 equals 0.5. Okay, here's another example. For mean equals 100 and standard deviation 10, what Z-score corresponds to X equals 120? Without using the formula, you can do it in your head to get Z plus 2. All right. Now with the formula, Z equals X minus the mean divided by the standard deviation. So that's 120 minus 100 divided by 10. All right, so it's 20 divided by 10 equals 2. Pretty easy, huh? Z-scores are fun. Here's another example. For mean equals 50 and standard deviation equals 8, what Z-score corresponds to X42? Without using the formula, you can do it in your head to get Z equals 1. Here's the formula. Z equals X minus the mean divided by the standard deviation equals 42 minus 50 divided by 8. So it's 8 divided by 8 equals negative 1. Okay, and let's see how to find the value of x using the same formula. It's just doing it backward. And because we're at about 14 minutes here, we're actually about 13 and a half, we're going to jump over to the next slide. Or not the next slide, but the next video. So I'll see you in a moment.